Hi, in this video I'm going to discuss a question related to electromagnetic induction. The question is shown on the screen. Okay, so according to this question, ABCD is a rectangular metal frame made of metal rods. The points E and F are connected by another rod that also metal. So this metal frame is kept in a uniform magnetic field which is directed into the board or into the page such that the field lines are perpendicular to the plane ABCD. The resistance of the wire is given like resistance per unit length is 1 ohm per meter. So that means the length AE 1 meter means its resistance is 1 ohm. The resistance of AD is also 1 ohm because that is 1 meter length. But the resistance of EB, part of the rod EB is a part of it. That length is 0.5 meter. So its resistance will be 0.5 ohms. The question is, now you know that when there is a rate of change of flux linkage with a metal frame, there will be induced current because of the induced EMF. So the question is, the magnetic field strength B is uniformly increasing at a rate of 1 Tesla per second. So that means rate of change of magnetic field strength is 1 Tesla. So when that happens, what is the direction and magnitude of the induced current on the sides AE, EB, and EF? That is the question we need to answer. Okay, so magnetic field is directed into the board and the magnetic field strength is uniformly increasing. So that means it is increasing at a rate of 1 Tesla per second. So, you know, according to Faraday's law, rate of change of flux linkage is equal to induced EMF. Magnetic flux is given by phi equal BAN, where B is the magnetic field strength, A is the area of the cross section, and n is the number of turns. So here only just one. So n is equal to 1. So here rate of change of magnetic field strength means delta B over delta T or dB over dt is equal to 1 Tesla per second. Okay, so here they are saying that magnetic field strength is uniformly increasing. So there's a rate of change of flux linkage that induce EMF. Since it's a metal rod, there will be current flow. So the according to Lenz's law, the induced current should oppose the increase in magnetic field. So the magnetic field is increasing into the board or into the page means induced current should oppose it. So the direction of the induced current, the direction of the magnetic field due to the induced current should be out of the page. According to Lenz's law, it should oppose the action. So the direction of the magnetic field produced by the induced current should be out of the page. Then only it can oppose the increase in this magnetic field. So according to right hand grip rule for field, if I consider on this side, so the induced current should produce magnetic field out of the page. Means, so the according right hand grip rule for field, if the current flow is this way, the magnetic field will come out. So I can see the direction of current flow here. I can make this I1, the current here I2. Okay, I'll make it as I2. This way flowing it. So the same current will flow here I2. So here I2, you can keep the right hand grip rule. You can see the field lines are coming out. Then they can oppose the increasing this magnetic field. So this I2, this also I2. Here the I2 will flow this direction. Okay, so in this square surface, there also the induced current should oppose the increase in magnetic field. So there the I1 should be this direction. Then only the magnetic field can come out. So I can show the I1 this direction. This is the way I1 should flow. Here the I1 should flow this direction. I1 should flow this direction. You can see that right hand grip pull for field. The magnetic field will come out. Here I1 should flow this direction. Okay, so on the rod EF, the current is flowing opposite direction, I2 due to this loop, I1 due to this loop. So we don't know which one is the largest current. I1 or I2 is the largest current. So I'll take just I1 is the largest current. So the net current flow on EF is equal to, I'll remove this and I'll put I1 minus I2. The net current flow due to I1 and I2 will be I1 minus I2 on this line. So I'll put it as I1 minus I2. This direction, I'm taking I1 is greater than I2. Okay, right. So finally, I am going to use Kirchhoff's second law. So we found the direction of the current flows by using Lenz's law, right? Uh, Now, I know that rate of change of magnetic field strength, delta B or delta T is equal to 1 Tesla or dB or dt 1 Tesla. We know that phi equal BA, so induced EMF is equal to BA over dt. I can say del T. But area is constant, so I can say A into delta B over delta T. Right. Okay. So now we'll consider this loop, the loop ADFE. We'll consider ADFE. So I'm going to use Kirchhoff's second law there. We know that induced EMF is equal to A into delta B over delta T. That's the induced EMF is equal to total, I'm going to use the Kirchhoff's second law. So sigma E equal to sigma IR. So that is equal to total IR. Okay, so area of this cross section is, the length is 1, width is 1. So 1 into 1, 1 into 1 into delta B over delta T, we know 1 Tesla. So that also 1 is equal to IR, the sum of the IR. That's the Kirchhoff's second law says. So this length is 1 meter. So resistance of this length is 1. So I1 into 1, because we know that resistance per unit length is 1 ohm given in the question. I1 into 1 plus here also I1 into 1 plus here also I1 into 1. Here I'm taking in anti-clockwise direction. The current also I took it flowing in anti-clockwise direction. So that will be I1 minus I2 into 1, because that length also 1. So we'll solve it. This is 1 equal I1, here also I1. So here inside I1, so 4I1 minus I2. So I can say 4I1 minus I2 equal to 1, the first equation. Okay, so now we'll consider the second loop, this one. We'll consider the loop EFCBE. So we'll consider the loop EFCBE. I'm going to use Kirchhoff's second law, the same equation, induced EMF equal to A times delta B over delta T, that's the Faraday's law, is equal to, I'm using the completely Kirchhoff's second law, sigma IR. So the induced EMF A, the area of this frame is, the length is 0.5 meters. So this is 1.5 meters given in the question. This is 1. So this is 0.5. So 1 into 0.5, that is A. Delta B over delta T equal 1 is equal to sigma IR. So on this length, I'll start from here, FC, I2, the length is 0.5 means the resistance also 0.5 ohm, because resistance per unit length is 1 ohm. So that is I2 into 0.5 plus here I2 into 1, because that is 1 meter length. This is 1 meter length. Here also I2 into 1. This is, I'm taking in anti-clockwise direction. So anti-clockwise direction means current is flowing opposite direction. So minus I1 minus I2 minus I2 into 1, because that length is 1. So solve this one. So that is 0.5 equal. So here 0.5 I2, 1 I2, so 1.5 I2, 2.5 I2 minus into minus, that is plus. So that will be, so this is EB I2 into 0.5. This is 0.5. So this is I2 into again 0.5 minus here I1 minus I2 into 1. So this is 0.5 this length. So we'll solve it. 0.5 I2 plus I2 1.5 I2, 2 I2, 3 I2. So that is 3 I2. In terms of I1, there will be minus I1. Minus I1, yes. So that is going to be minus I1 plus 3I2 equal to 0.5. So multiply by 2, you'll get minus 2I1 plus 6I2 equal to 1. That could be equation 2, the second equation. Okay, so I need to solve only these two equations now. Okay, so the first equation is 4I1 minus I2 equal 1. That is the first equation. Second equation, minus 2I1 plus 6I2 equal 1. That is the second, this is the first equation, this is the second equation. Okay, so you know how to solve. You can solve it by using calculator or manually. So to solve manually, I should multiply the first equation by 6. If I multiply, I will get it 24I1 minus 6I2 equal to 6. I'll take it as third equation. Okay, so by using second equation and third equation, I'm going to find the I1. So add second plus 3, I will get 6I2 plus 6, they will get cancelled. So 24I1 minus 2I1, 22I1 is equal to 7. So I1 is equal to 7 over 22 amperes. So 7 over 22 amperes means that will be 0.318 amperes. 0.318 amperes. So that's the current flow on AE. The direction will be from E to B. The direction of the current, I can say E to B. The direction of the current E to B. We found it by using Lenz's law. E to B. So I found that current. Okay, so first one I found it, answer. Then I need to find the current on EB or B2, BE, that is I2. So I can substitute the value of I1 in one of those equations. I'll substitute in equation 1. If I substitute, I'll get 4 times I1 is 7 over 22 minus I2 equal 1. So I2 will be equal to, you know that, 28. So 6 over 22. So that will be equal to 6 over 22 means that will be 0.273 ampere. The direction will be, we found it, I took it from B to E, I'm getting a positive answer. So that means that's the direction of the current flow, B to E. So that is the current flow on EB. That should be from B to E. The value is 0.273 amperes. Okay, so the last I need to find the current flow on EF, whether it is going to be E to F or F to E. I took it F to E, we'll see. So that is I1 minus I2. So I1 minus I2, I need to find it. I1 minus I2. So I1 is, we found it 7 over 22 minus, the other one is 6 over 22. That is 1 over 22. 1 over 22 will be 0.045. So that current direction F to E, that's the direction. So we found all the answers. That is I1 minus I2. That is I1 minus I2. Okay, so that's the answer of this question. So we found all the three currents. on AE, EB, and EF. The directions also given. We found the direction by using Lenz's law. We used Faraday's law here, Faraday's law in this one, and also we used the Kirchhoff's second law. Okay, I hope you understood this question. Yeah.